All right, so this is this is probably only of interest to the observers in the room, so I'll make it very quick. But I was asked by a few people what's kind of the latest and greatest in how we're communicating our events. So over the past few years, I've spent a lot of time trying to develop the communication standards for fast radio bursts. And we originally were doing this through VO events. So these are these XML text, basically messages that have all of the information encoding information about a transient event. So it's not about a source, but it's about a transient event. And we built this up over the past few years so that you could send VO events out over this already well designed network, and then we would parse them and ingest them directly into the FRB catalog. That functionality exists and it works, but no one has issued live VO events yet. So maybe we'll never have it happen because our plan for is that by the middle of this year, we're going to switch over from VO event based system to keeping all of the FRB events on this transient name server, or TNS. So the TNS is already being used to name and catalog supernovae by a lot of and a lot of other types of multi-wavelength transients. And one of those kind of strengths of the TNS is that it's a central repository that you basically you can keep your events private there. That they will go public when you choose for them to. But you basically consult the TNS for a name for your source or for your event, and then your event gets this centralized name. So we would have all of our FRBs named under one naming scheme, and if there's multiple FRBs on a given day from different telescopes, the TNS takes care of what those events are called. We don't have to worry about if there's like three FRBs that everybody starts with an A, for example. This is work that's being done at the Weitzman Institute. It's funded there. They have actually like staff who work on this, which is really nice. So I just wanted to show a little bit about what's being built for FRBs. This isn't live yet. It doesn't work out in the wilds of the internet, but this is the sandbox version that we're currently prototyping. Yeah, so you might want to. So this is what the TNS homepage looks like. This is the sandbox. So we're really just we're in the beta, and it's a very simple homepage, but essentially you can upload events. So you can upload these things called reports. And so AT is just an astronomical transient report form. There's also a report form if you have a classification of an event. And now they've added this new tool called an FRB report form. And we've worked with them to try to make sure that all the parameters that we care about are in here. But that being said, we're still working on this. And there's, I think, a Google Doc has been circulated to a lot of people. But if you haven't gotten that and you're interested, you should tell me and Vicky. But anyway, so there's coordinates. You can add your reporting group. So Chime FRB is already in here. Craft is already in here. But you can add who you are, what type of discovery data you're selecting, and then the internal name at your group, all that stuff. We have all of the basic information. One of the nice things is that we're starting to build in this like a region ellipse for the error region, rather than just having like an RI deck and an error on that. Apparently that was not the right thing to do. And you can upload even like a region file that has the error ellipse in it. So then DM error, and then you can also upload. There's lots of like nitty gritty, and so we've also tried to build in things like the structure maximizing DM and stuff like that. So hopefully everything is in here, and you should just be able to, if you just have one FRB, you can come and plunk all this stuff in the form. But you should also be able. Oh yeah, so you can add some other files. And you can add more events, and then you submit your FRB report. But you should also be able to, and this is the part that I haven't really tested out yet. So this is going where I have not gone before. You should be able to also upload and like just do a batch upload of events. So if you have like a large catalog of events that you want to put in, you can batch upload them as well. So the hope is that each team would come to this webpage, upload all of their events to get designated names for them before they publish. You can make the events proprietary for a specified amount of time. And then when you do publish, you can then make them public on the TNS, and it'll be basically a searchable repository for all of the FRBs. It'll replace the current FRB catalog. And it will replace the current reporting system that we have. And then you can also, if you have an account with the TNS, which we all should when this is up and running, you can also subscribe to event alerts. So you can say specifically in your account, like what type of alerts you care about. So you can say, I care about FRB alerts, and whether you want to get those as like a daily news digest in your email or whether you want to get them right away. And that stuff is all still in testing as well. But I just wanted to show what we're working on. Hopefully by FRB 2020, which is in like a month and a half, this will be much more developed. It will have something that everybody can play with, and hopefully we'll have some people from the TNS at FRB 2020 to walk us through the whole procedure. But I just wanted to give an update. Yeah. Yeah, I mean, there's a kind of an issue with this as well because of like the PTF people and other supernova people basically put every single candidate they have in the TNS, give it a name, and then they only make the ones that are real public. Or they can retract stuff later, but that's how you end up with these supernova names now that have like 4 letters after them. It's because everybody's just putting every single event in there and it gets its own little designation. So so it'll be like that. Daniele?
Since you have an APA, I guess is it also possible to like automatically upload through a script? I mean,
Yeah.
after the telescope detect it.
Yes, it should be possible to automatically upload. Maura?
Upload data, like say like a polarization profile?
That I don't think that they're really keen to keep, but I think they're trying to keep the actual amount of information that's stored in their database kind of bare bones. But I think if we go back to this report form, there is you can let's see if I can find it. You can specify like your web page and stuff like that. So if you have a link to data on your own web page, I think you can link to it here.
And just a second question.
Yeah.
Like if you have 2 surveys, they both find an FRB like the same day, which would have the same name otherwise, but they both want it to be proprietary. Does it still like compare the names and tell the teams like, hey, yours is A and yours is B?
Yeah. So I could submit an FRB and it could give me FRB 2020 02 07.
Okay. You would know another team found something that day.
And I would know that there have already been 2 things submitted already. So, but that doesn't really tell you much besides just that there are other FRBs out there. No, you don't get positions or anything like that.
It depends how we name FRBs. If we started naming them with the positions, then
yeah, I mean, I think the naming scheme that we've come up with them is really to stick with the year, 4-digit year, month, day, and then letters. Right. Yeah. So, Shami. Yeah, so I think we haven't really gotten this far yet, but the plan is that the TNS will not only host events, but will also host sources. So you can group events into a source. So for example, if you have multiple pulses from a repeater, then the repeaters will also get their own designated names, I believe is what we're hoping. And so eventually if a source is found to repeat or multiple events are found to be from the same source or even the same FRB, they can just be grouped into one named source. So. Yeah. That I don't know because I'm not managing the database side of things, but this is something that we can ask the TNS people. So yeah, Johnny and then Kendrick.
I was just going to say, coming back to this issue of like storing other data, I know for supernovae, they often do like spectra and light curves and stuff like that. I don't know the details, but.
Yeah, so we've talked to them about like, it's kind of an interesting problem because they're just not familiar with our data. They definitely aren't interested in storing like images or like waterfall plots or stuff like that. But I mean, a polarization profile, I guess, is pretty low information. So that could maybe be something that they would store for us. Kendrick, you were waiting for a while.
I was going to ask about grouping events associated with.
Oh, okay. Okay, I won't take up any more time on this. If you're interested in being involved in this, I think just let me know, and I'll put you in touch with the TNS people. They're definitely the ones to talk to, not me directly. And then hopefully we'll have a clearer picture of what this is all going to look like in practice in a month or two. So that's it.
Thank you. Hi, I'm Xavier Prochaska, UC Santa Cruz. Nice to meet you all. Before we get back to the future, I wanted to take a minute to recognize the organizers. I don't think they've been given that opportunity. I'm not exactly sure all of who you are, so please stand just to make sure we get you all. Let's please give them a round of applause. Sure. Bring them on in. I've been asked to lead this future discussion. For those of you that don't know me, I tend to study gas in the distant universe using optical and UV spectroscopy, and I'm quite new to the FRB field, but I've been sucked in on those scientific grounds. And the panelists, where have you all gone? You might be okay. You might be wondering why I'm presenting or leading this discussion as much as I am wondering that. It's possible that it's because I'm a bit of an outsider, and so I have a fresh perspective and no particular biases. I don't have a horse in the race. I've probably learned more about magnetars over the last 3 days than the last 20 years. Nevertheless, just keep in mind I'm a bit of an observationalist, and I'm going to be relying on the panelists to be leading this discussion. I'm just mainly the moderator here. That said, I have a few questions that I'm going to propose to them, and hopefully you have to, because of how few you are, the crowd needs to jump in as we go as well. So here's a 2-slide summary of what I've taken from the meeting from my high-level or whatever outsider perspective, however you want to call it. I'm giving short thrift to the theorists, but I was convinced multiple processes can satisfy the key observables that define FRBs, which you can say in a positive way FRBs can exist. The theorists have proven it. That's a good thing. I was also persuaded that at least the current mission models are not very well constrained by these properties alone. And that clearly leads to a lot of the discussion and a lot of the open-ended questions as it comes to what are the engines and the emission mechanisms that drive these events. From the observations over the last few days, we've seen clearly that there are now order 1,000 FRBs detected mainly across the northern sky, with dispersion measures extending to several thousand DM units. That's exciting to me. I think that's clearly showing that they're being detected well. Well, previously been known, but even clearly more known that they're being detected well out into redshift 1 and beyond. I think we're at the state where still the number of measurements of RM and polarization and widths are pretty small. But nevertheless, what does exist shows a pretty large diversity, pretty large range in value. And it's still, I think, quite early days for distinguishing between what fraction of those measurements are intrinsic to the event and due to propagation effects. Lots of discussion on counterparts. I think we have none compelling today, electromagnetic or otherwise, but clearly there's an emphasis on pursuing that more aggressively going forward. We've seen about roughly 10 hosts associated with the FRBs. They're primarily star forming. I think all of them really have some emission lines. Whether it's star formation or something else remains to be seen, with offsets ranging from a few to 10 kiloparsecs and primarily in more massive galaxies. And from I was drugged into this at some level by FRB 121102, as maybe some of the rest of you were. It's becoming clearer to me, at least, that it's not such a representative event, despite the fact that it still holds high value in driving this field. Where do I see? Here's where I think securely the field is going in the near future, of order 5 years. There'll for sure be thousands of events detected across the northern sky. The high time resolution is going to be applied to, I think of order 100 events, maybe more, over the next 5 years. and probably roughly 100 associations to fast radio burst host galaxies with redshifts that come with them. I think the VLBI searches and similar are really exciting. Maybe they'll be of order 10 FRBs localized to milliarc second precision. We're going to definitely see faster, deeper, wider searches for counterparts. I've stolen that name from the FDW search that does exist, but I imagine there'll be other surveys cropping up now. And along the way, I'm sure there's going to be more oddballs. That's, I think, what keeps this field exciting. And I don't want to cast them as too negative. That those extrema can often be very valuable for killing theories or pushing theories into new parameter space. But there will be I think the promise to distinguish what is somewhat odd from the normal. I didn't hasten to predict what theory will bring in the next 5 years. I suspect there'll be another 10, 20, 30 models, fine. But we're clearly seeing some exciting advances on the astrophysical side as the modeling becomes more sophisticated. All right. End of said summary. These are the 3 questions I'm posing to the panelists in the audience. Probably will take them up in order if you wish. On what future science what future science or empirical advances are you most optimistic or pessimistic? If you want to rephrase that in New York City lingo, Wall Street lingo, where are you bearish or bullish in investing on what advances will take place in the next of order 5 years? What are the real key limiting factors and challenges? Where should we be putting our efforts? How do we mitigate those? And then I have some additional thoughts we've heard from the previous future talks about working together. Where should we and where can we work together to more effectively pursue these science? So, panelists, come on back. And anyone can jump in from the audience as well. So as far as science or empirical advances in the next N years, 5 years, let's say, where are you optimistic, where are you pessimistic, and why? The audience can hold their own opinion. I've listed a number of things that you could comment on, but you're welcome to fill in your own in the blank.
Hello, sorry, this is Maxim Rydikov speaking. Can you hear me?
We can.
Can I express an opinion on the future prospects?
Absolutely, please do.
So I think one of the biggest hopes we have is to detect FRB at other wavelengths. And as I was arguing earlier today in my apparently scrambled talk, there is almost no hope to see FRB at X-rays because the energetics would be, the required energetics would put them into gamma ray burst type category, and the rays don't match. So we know that FRBs will not show in X-rays. Our best hope then is to see them in optical, meaning if we have, say, the repeater at 10 to the 40 ergs per second in radio, perhaps it will put 10 to the 45 in optical. 10 to the 5 in optical would correspond to a 9th magnitude star, but only for a millisecond. Typically, the wide field surveys have about 30 seconds exposure, so that would be about a 20th magnitude object. But of course, there is so much noise that it will be 20th magnitude 1 pixel signal will be discarded. So then the game is to have a simultaneous shadowing observations both in radio and in optical. And modern optical telescopes can have about 10 square degrees, and the expectation rate of coincidence is about 1 per 10 hours. I would argue that the best strategy would be to look at the same location, say Palomar and Chime, they kind of almost can get a look at the same location, hoping to catch simultaneous event. Yes.
So MeerKAT has the commensal program MeerTrap, which is going to be looking at the same direction as MeerLicht in South Africa. So I know you're in America now, Maxim, and we know about geography, but there are continents outside of US.
Yes, the question is, simultaneous radio and optical.
What?
Yes,
Yeah.
if Meerkat could.
Yeah.
Well,
So Meerlicht is optical, and it's going to be tracking the field of Meerkat 100% of the time when it's dark.
So
oh, excellent. That's news to me, and I think this is the strategy that we need to pursue. Yes.
let me ask this question, which I almost raised yesterday. Why start with commensal survey? Why not just aggressively go after the well-localized repeaters? You know where to look. There's no question of a coincidence anymore.
Oh yeah, of course. But
So the short answer is for the first repeater.
catching an FRB as simultaneously at different wavelengths, that would be a big thing.
Please, Laura.
So for the receiver repeater, we've tried this with various high sort of cameras that do sort of 10 millisecond imaging. For close to 3 years, we've been trying to do this with any radio telescope and the HyperCam instrument on Grand Tran and the Canary Islands, and we have yet to actually have good weather and radio detections at the same time. And we have tried at least half a dozen times. It's been very frustrating. Our 3 is obviously the next one to try, but that's only been public for a couple of weeks. And but in the course of this year, early next year, we'll, I will be working with people to do this. So, and obviously, as more are localized, we can go after them as well.
And how strongly do you need the contemporaneous? If someone were to point, a 3-meter class telescope at the repeater location for 5 days in a row for 30-second exposures, obviously if you see nothing, you'd have some concerns that there were no repeats during that. But still seems like a worthwhile experiment and pretty straightforward one to pursue. Yeah.
As a naive theorist, again, I think this question was raised, but is the noise in these, on these timescales in the optical characterized? Do we know how to distinguish whether we see something if we just blindly stare?
You're not going very shallow. I'm sorry. You're not going at millisecond cadences in this case. It would just be tens of seconds, and yes, that you can characterize very well.
No, but I mean, we still can. Adaptive optics cameras, for example, the wavefront sensors work at very high speeds. We have EMCCDs which work at 1 millisecond time scales. And I mean, there are things which happen, but it can be done. And so maybe Ellie can add to this. So Eran and others have been working on Kuiper belt object occultations of stars. So they look for very fast Fresnel fringing when the Kuiper belt objects go across the stars. And the idea there, the need there is the same. You have a wide field, fast camera, and it has been done. It's a high data rate, but it can be worked with. And especially for R3, we know the location. Like for when you say, okay, I just want to see if the flux changes in this location, it's not that hard.
Right. So the theorists optimistic we'll see something. Sounds like the experiments are going to get done. Which among the theorists are optimistic will detect anything? Nobody willing to stick their neck out on? Yeah.
Well, so
Please.
if the fraction of radio energy is very small, then you have a good chance of seeing it. If the fraction of radio energy is significant, so that in other wavebands these events do not emit much brighter signals, then you probably will not detect it. So
Yes, we only can hope
at least 1,000. Yeah.
Yeah, we only can hope that FRBs emit an optical. And as I mentioned, if it's 10 to the 40 goes in radio, our hope is that 10 to the 45 would go into optical. We don't know whether it will or not, but yes, it will be many orders of magnitude more.
Yeah, it seems like with each new kind of FRB property, many of the models can explain that property, with small tweaks to the model. And I'm just wondering if, say, there was an optical pulse detected coincident with an FRB, like would that actually rule out any class of models entirely?
I would say that
how much extinction do you expect towards these sources?
Sharsh?
Might be extincted for I mean, if you have local, given the current the galactic magnetars, but for R3 it is a face-on galaxy, so you don't really expect, other than if there is a shroud around it, I wouldn't expect too much.
All right, let me shift to another bullet. I'm going to request this one from the radio astronomers. We've heard some very exciting or interesting next order measures and strong wave effects. What are the optimism from the observational side of things of detecting those in the next few years? Now that you know what you're looking for.
I mean, I think that I'm talking because no one else is. I think you'd probably say similar things, but I think measuring like next order measures on DM, making really precision measurements on DM is really, really difficult, given the very complex frequency structure. Even this kind of stuff is really, really difficult for pulsars, just because of pulse profile evolution with frequency, and they don't even show any of this really funky frequency structure. So I think that's, I don't know, I think that's very, very difficult. I'm not very optimistic that that could be done easily over the next several years.
But don't we already know from even the pre-CHIME era that the index is like within 10 to the minus 5 or 10 to the minus 4 of cold plasma dispersion? And with CHIME, when you've got all this lambda squared coverage, you can do better than that, right?
Yeah, but the deviations that you'd expect are smaller than that, right? The ones that are interesting to test for, aren't they?
No, I mean, if a significant amount of the dispersion is coming from within like an AU, where significant means 10 or 50 or 100, then you can pretty easily get deviations from -2.
I think the bigger question is, if you do see deviations, would you be comfortable attributing them to actual plasma deviations and not a pulse profile variation?
Yeah, true. I mean, you might get lucky and have free absorption, because this is the EM term after all.
I was going to mention. So I mean, Andre said that he thinks this paper is wrong now because of galactic scintillation. But I mean, it doesn't mean the paper is wrong. It just means we see an effect in the data, a correlation bandwidth of 50 kilohertz that. It fits with what we would expect in that line of sight. That doesn't mean that that's the physical origin of it. I mean, it's possible. It seems like the most likely explanation. But I mean, if you look outside the galactic plane, the scintillation bandwidth is really quite radically different. And if you were to still see structure on 50 kilohertz there, then that would be more interesting. Well, I mean, I am Canadian, but but as a scientist,
he's not that nice.
Yeah, I'm not that nice. I mean, Matthew knows better than.
Yeah, I would say that I was interested in your talk because for the ASCAP FRBs, we see structures on the order of 20 megahertz that, it's kind of 50-50 whether or not it's scintillation or not. So can your model predict 20 megahertz? Well, so we need to really,
I hope I was honest enough.
Yeah.
I tried to calculate what nonlinear things would do. Maxim Lutikov and Yuri Lubarsky correctly say there can be other kind of stuff going on. That's right. That's just a hope. But I think for conversion measure is not even our invention. After we wrote the paper with Levin, everything was done in the 60s in Russia, of course. So it is Zheleznyakov and whatever, all these classical radio astronomers. So this effect is. The question is, will they be able at 500 megahertz with the resolution of 0.01 megahertz measure this stuff? If they do, it will be very strange if they don't see any Stokes V with this fine structure. But I don't know, of course, I don't know. I tried to ask when I was talking the Laura and others, and they are not giving straightforward answer, just saying it's hard, whatever.
Changing topic slightly about the lensing stuff. So there's this sort of, I say controversy in LIGO, but there were these claims that LIGO's black holes were lensed. And I guess I was curious. I don't know anything about lensing, but I guess I was curious: will FRBs be able to weigh in on this? Namely, if that were true, and there were so many gravitational wave lensed events, that you would see much higher fraction of events. Anyone have an opinion about that?
LIGO sees the sky all the time, and none of our telescopes do. But we get a lot more events. So
I was just thinking about like density of lensers or whatever one wants to say. Yeah, no, I understand. You're not seeing the same events. I guess I'm asking more like the statistics of lenses and things.
Are there other explosive transients, EM explosive transients that could potentially be lensed, or just strong galaxy lenses or something like that? The claim was that like a half of black hole mergers were gravitationally lensed, right? Yeah. But I feel like it depends on them being in like the wave optics regime or something. I think you're better off just using lensed AGN or something.
Jason?
Yeah, so related to what you're asking, Brian, and also related to what Andre was talking about, the various measures and whatnot, I think observers need to become a lot more professional. I think every paper, people use slightly different language, slightly different analyses, slightly different metrics. We really need like a master's student or a PhD student to just create like an FRB metrics machine where you say, take voltage data, put through machine, and we'll produce a consistent set of numbers and things that we've measured for that burst that everyone understands what they mean. And I don't think any of these things we're going to, with one burst, say, oh, we've detected gravitational lensing, we're done. This one, I think we need to build up a lot of statistics and look for where the patterns are compared to what you expect from the Milky Way foreground and whatnot, and look for where there are obviously deviations. And we just have not worked in that systematic way yet.
Gravitational lensing, I just want to quote a crazy idea proposed by Roger Blandford before he left. I don't understand what it means, I will just repeat it. He is saying that if you have a lensed event, and if this event had very fine structure in time, and it was coming from whatever gigaparsecs, then Blandford proposed that it can become a gravitational wave detector competitive perhaps with PTA. I don't know what it means. I'm just repeating some crazy thoughts of a great man.
Yeah, maybe he thinks the two paths are like arms of an interferometer. Or
the two paths go through different parts of a gravitational wave, a long gravitational wave, like pulsar timing array kind of gravitational wave. So they both will have an imprint of Shapiro delay from the gravitational wave itself.
With different things.
Yeah. So in the coherence, maybe you can pull that out. I'm guessing that's what he's thinking.
It would be degenerate with a delay.
It would need to be a frequent repeater.
Because there is a wave. So if you get repeat bursts,
you need a frequent repeater.
There's a wave moving through the.
But this is a contradiction because now you're saying that you have very low frequency gravitational waves, but you have fast bursts of radiation. I mean, this doesn't make any sense. If you need to get these really long period gravitational waves.
No, imagine there is a long wave, right?
Pulsars are in the galaxy. FRBs are in the universe. It has much longer.
Are you saying that the pulsar? I'm confused now. What am I detecting?
Light has travelled through two different paths with different gravitational wave backgrounds on either way.
Sorry, what's the source?
The FRB. But it's gone
FRB,
two different ways.
Okay.
So it's experienced two different potentials, if you like, of
yeah.
gravitational waves. If they vary rapidly,
and then you now wait for the wave to move, and the repeat burst will go through different parts of that wave.
So to speculate wildly on Roger's point is,
like how Roger's managed to.
Yeah, if you had multiple FRB sources that had this like microstructure, and your measurable is the, you know, instead of a like a
Residual?
instead of a residual, you have something like the time spacing between these microstructures. Then I guess you look for correlations there. But
in the way Harish is describing it, you just look at the change in delta t between the two images of the same burst. It has to be a repeater, and then you say, well, this gravitational wave has passed by, right?
Didn't speak to Roger, but that's the first thing that comes to mind.
I'd like to bet that we will not detect a gravitational wave lensed FRB in the next decade.
Hey.
If anybody wants to take me on.
Yeah, thanks for your pessimism.
But isn't this also completely? I mean, the thing which people were trying to do with the change of h naught with time, right? The cosmology which people are trying to do with lensed FRBs. This is completely degenerate with that, right? And the intervening halos moving around
and all sorts of other things.
Yeah.
I assume, so.
Okay, never mind then.
Can I suggest like a question? Like in terms of planning future observations,
Only
I
if
think
you use your microphone.
Yeah, I am. It's on. So in terms of planning future observations, I think it's useful to ask people who are doing theory what observation would make them like throw away their favorite toy and then
I
say
almost
it's
added
dead.
that question.
Yeah.
That's a good one.
Yeah.
All right. Brian left the room.
Noticed, yeah, I was
wisely.
Brian's giving a talk on the other side of the street.
Oh, cool.
Yeah.
Repeat your question for those that probably didn't hear it. For those of you proposing a model and mission mechanism, what observation would kill it on the spot? Or would you be willing to sign up to that would kill it on the spot?
I mean, so there are a bunch of different predictions of at least our model. So you know, one example is these counterparts that in our scenario of the model should be gamma ray counterparts. Detect something in optical, or you put upper limits where you don't detect anything. That severely constrains this scenario, right? Thinking about the environment and persistent sources in rotation measures, if the emerging picture continues to be that we detect none of these, then maybe it's time to rethink that picture, right? So there are various predictions that the models make and easily falsifiable. But the flip side is that there are, I think, plenty of models, certainly if you just browse the whatever 50 so models in FRB Theory Cat, that make very little predictions, and so they aren't as easily falsifiable.
Make you toss away the non-magnetized.
Something that would make me toss it in, but it's so. I mean, we call these models, but they're not really models. They're not full calculations of anything. So, okay, they're sort of suggestions. But maybe you should sort of ask for a more limited or less ambitious goal, which is to try and identify progenitors.
Mm.
What type of observations would help you identify progenitors? And I think that the environments, so the localization of the environments, and one thing that you did not, maybe two things that you did not write. One, I think you should ask what is the probability to detect a very nearby event, and what is the best method to do this? Maybe this should be a significant effort, and the other is the possibility of detecting other persistent sources, because if we have a nearby persistent source, I guess we can learn a lot more about
What are the prospects of pushing down some of those limits? We saw a plot or two that showed, there were a handful below, I guess, the repeaters level, but what are the prospects? Are people going to pursue those more aggressively, or is it, given those the likely redshifts are not worth the time? Yeah.
I think we have to define what we mean by a fast radio burst. So is a crab giant pulse a sort of nano FRB, and do you just keep dialing up the knob and eventually you get to FRBs? I mean, is that the tail of the distribution, and therefore have we already detected them? And what can we observe that would break that degeneracy between a nano FRB like the crab and a real FRB like the Lorimer burst?
So one thing that's not on the list that
haven't heard anyone talk about is looking for strict periodicity. Right, I'm distinguishing between what we see in Chime R3, where the periods of activity are periodic, and the actual arrival time of the pulses being strictly periodic, like coupled to the rotation of a neutron star. Is that because everybody is too pessimistic that that's going to be observed? Or? I mean, that would, for example, distinguish like the crab giant, a model where FRBs are crab analogs, from something where the pulses are not tied to the rotation of a neutron star.
So to comment on Matthew's question, I guess I would think that until you filled in the gap in implied energy between giant pulses and FRBs, we would treat them as a separate population. And once we had enough to fill in the gap between them, then we would start talking about different populations that are bleeding into each other, I guess. That'd be my initial thought. So until we have objects in the gap, they're distinct populations. Maybe that's because we haven't looked hard enough in the gap yet. Yeah, I missed the question about periodicity.
I'll rephrase it. Why has there been not so much discussion about periodicity at this meeting? Is it because the result's too new? Is it because you're all concerned it's not quite secure, or is it?
Oh, are we talking about rotational or orbital periodicity?
16 years. Yeah, something about rotational periodicity. That's like
so, like seconds, milliseconds kind of periodicity.
Like,
yeah. No, I think that for the one object where there's enough to be to have fairly stringent constraints, probably is 121102, and there at least so far searches have been unsuccessful. So far, I mean, maybe someone else comes up with something, but it is not Poisson, is it? No, it is not Poisson.
Is it Poisson when it's active?
But do you think we've learned our lesson a little bit too well from 121102? Like, I think because we have all these pulses from it, and there's still no periodicity, and so we're saying, okay, it's impossible. We should be throwing 121102 out of every single thing that we do with upcoming FRBs. Like, all of the analysis should pretend that burst does not exist, because I'm serious because we're so biased now, because we just expect everything to we have expectations that are set by this source, and at every turn it turns out to be an outlier. I mean, like the sad trombone thing, whatever, that's there, but I think it's truly exceptional in so many ways that we should be kind of, when we start to analyze a new source, we should be kind of just ignoring what 121102 does and do it kind of more blindly.
Are the repeaters on as often as FRB12?
No.
Much rarer?
Yeah.
And
so it is outlier in this respect too. Okay.
Well, so far,
and also I don't have all of them.
Is that really true? I mean, Chime has seen like about 30 bursts from R3 and 1 burst from R1. So why is it obvious that
it's not obvious? Yeah, I mean,
but in a
it's
given
also,
session,
it's a completely different. So Chime observes only for 10-ish minutes at a time. So there is no one session per se, and and it's a different frequency, it's a different sensitivity, so it's not a apples to apples comparison at all.
Yeah, R1 hasn't repeated at Chime, right? So
yeah.
So that you could argue that all the ones that have, the other, is it 13 or 20? I don't know.
Yeah.
If anybody's allowed to tell me, then fine. All those you'd say were repeating more often, but they're probably closer and lower luminosity also.
Yeah, because R1 was discovered with Arecibo, so
So just for the theorists, I guess, is even though the Chime ones have multiple bursts, they don't have multiple bursts in a given observing session, and then it's really hard to fit for a rotational period when you have sessions with gaps, because you can't be sure of your clock coherence across those gaps.
I wanted to comment on the comparison between R1 and R3. So R1 is not a repeater at Chime, I think primarily because we get 4 minutes on R1 every day. So it's even if there is some clustering or there is some activity, you don't even have half an hour or an hour to cash in on that activity, and then we see it after 24 hours. Maybe the active phase is ended by then. Yeah, so it's not a good comparison in that we get at least 4 days of activity window with R3, and we can like capture the source 4 times during that window.
And we have seen multiple bursts like that.
So Emily and I had this paper, I guess a year and a half ago now, where we suggested even though it's a long shot, you might as well do periodicity searching on once-off FRBs. Actually fold them, and it was kind of based on Moore's and Jim's paper from 2003, which showed the regimes in which it's actually signal to noise optimal to do periodicity searching versus single pulse searching. So for certain values of luminosity function and certain values of the number of pulses in observing and in a pointing, you get a lot more signal to noise out of folding. So, it's not a crazy thing to try.
Actually, on that topic, how bullish or bearish are the audience on in the next few years, knowing whether, at least in the FRBs that Chime can detect, whether the majority of them are repeating or not repeating? I'm gonna put you on the spot, Liam, because you put a slide up there that caught my attention. How confident do you think you will know that number within 4 years?
That fraction f, which again is the fraction of events that you've already seen repeat at Chime, is still only 0.5% or something. It's not growing very quickly, so I don't think it'll be known in the next 4 years. Well, maybe it'll really asymptote to like 4% or something.
Or if it stayed low, can we conclude that the majority of FRBs Chime is seeing is not repeating?
Not repeating on time scales longer than whatever. The problem is Chime only has 60 hours on each source per year. So even in 4 years, you don't get a great constraint on the repetition rate.
But this is kind of tied into the question of what's the luminosity function of FRBs, right? Isn't that? I guess that's the question. Will people in the next 5 years know what the luminosity function of FRBs are, or is?
I mean, the first thing I thought of when I saw your slide about the repeaters versus non-repeaters is also just the question of the spectral signatures. And like in the Fonseca paper, all of those repeaters have that very kind of funky, maybe not necessarily a sad trombone spectral signature, but these very narrowband features that I haven't seen in the non-repeaters. And I'm wondering from the Chime people, are there, if you can say, are there repeaters that do not have those narrowband spectral signatures and look like the non-repeaters? Because it would be really nice if there was a very clear, property to sort of hang your hat on as to whether something was expected to repeat or not.
I can comment on that. So we have not seen any repeater burst that spans the whole Chime band. But the bias of our detection with the beam response, the spectral beam response, is that you always push towards narrower frequencies. So you can only make the inference like one way. No repeater burst has shown up broadband, but probably a lot of broadband bursts show up narrowband.
Can you compare the broadbandedness of the repeating burst versus the non-repeating bursts, at least?
Oh,
or the non-repeater is more likely to be broadband, at least, with Chime.
Definitely. Yeah. And that's definitely something we're working on. It's hard. Like we commented on in the papers, it's a striking difference. If you just look at all the waterfall plots, it's like, oh, none of these repeater bursts spans the whole band, so something must be going on almost. But the hard thing is now to quantify that statement and correct for all the biases. With injections, it will be doable to answer it.
Repeater bursts are also a lot lighter than non-repeaters. Maybe I want to sort of comment about. I think we should ask what are the main questions that should be answered and why. And so there is a question of what is the plasma physics mechanism responsible for the production of these events. And this is an interesting plasma physics problem. And if I would make a bet here, it is unlikely to be resolved in a short time. We have the history of pulsars where there's much more data and you know much more about the sources, and the mission mechanisms are still debatable, okay? And for the same reason, it's also unlikely that from looking at these properties of the burst, you would be able to identify the progenitors. The second question is, that may be interesting, is what are the progenitors of these things? I think, and the answer to this question is interesting if the FRBs are telling us something about new types of progenitors. So they are compact, so they're almost certainly neutron stars. Okay, so what is interesting here? That it might be very interesting if there is a new channel, a different channel, producing neutron stars compared to other channels that produce other things that make these very bright FRB sources. And in order to answer this question, I think, which is to me is the more interesting one and probably the one that may likely be answered, is by looking at counterparts and identifying very nearby events that can be studied much more deeply and looking at the environment and so on. And I think this is somewhere where direction where more progress can be made. And I think it's more likely to come from this direction than from trying to figure out the exact physics of the plasma that produces the radio properties. Although most of the people here are radio sort of observers, I think the focus should, in my view, be more trying to identify the counterparts, trying to identify the most near events and these directions rather than.
So are we lacking in that activity? I think counterparts is just building up. I think, but for sure, probably everyone here wants to do the localization environments. I don't think there's going to be any lack of effort in the next few years in that domain.
Well, I'm not sure that there's a focus on trying to detect the nearest ones and to have contemporaneous observations in optical and fast optical. And so I think this should be the sort of the.
Casey?
I find it very instructive to think about counterparts in the context of like volumetric rates of sort of anomalous classes of objects. And so that's why I'm excited about the strategy that sort of Terene and I have been taking independently to characterize certain classes of anomalous things out there and think about if those the rate of occurrence of these classes are somehow matched to FRBs. So the reason that's been ambiguous in the past is that FRBs are very high implied volumetric rate. But if we get to the point where we can start to subclass FRBs, then maybe we can say there is a volumetric rate for repeaters, which is ambiguous because we don't know repetition, but there's a volumetric rate of non-repeaters, which is better defined. Then you can actually start to draw lines between certain classes and the non-repeaters, perhaps. That's very much more robust association. And like things like sky surveys are a big part of that now too. We can make that inference better.
Yeah, so obviously to find the nearest one, you want to go sort of wide and shallow.
Wide and shallow, right.
So one thing we can consider doing is doing subarrays, for example. So instead of taking your favorite interferometer and instead of pointing all the antennas in the same direction, take 4 of them and pointing in one direction and whatnot. So, I mean, it's technical work. I mean, I guess that'd be feasible with the VLA. Yeah. You're fine, I think. But yeah.
So I wanted to bring out another point which is slightly related to what Casey said about the volumetric rates. We search for FRBs integrated over the band. We don't really search for extremely narrow band events. So for example, if you look at the Farah et al. Burst, there are structures which are extremely bright over very narrow bandwidths. And if you raise the noise level, that is the only pixel which would be detectable above the noise level, and we basically miss those. So it is possible that there is a sea of these other bursts which are energetic but we don't really see. So
yeah, I think if there was a population of 1 megahertz wide FRBs, we would struggle to differentiate that from RFI, except if you had an interferometer of baseband data and then you could go, oh, it comes from over there, and maybe I can see microstructure if I coherently de-disperse it.
And so the volumetric rate of FRBs might be much higher than what we think it is right now.
Yeah, and just as a instructional story, I mean, like in the early days of getting bursts from the Arecibo repeater, a large number of candidate bursts were just put in this looks like strange RFI category because they were too narrow band that they didn't look the way they should.
In fact, well, it's just on his burst that he referred to. So the Farah burst was 140 sigma in 2 megahertz. And then if you integrated the whole 30 megahertz, it actually went down to like 120. So we're actually diluting it. And I'm sure that there is lots of FRBs in historical parks records that if you did little subband searches, they would get above the threshold. But whether you had enough DM to convince yourself that it's extragalactic is another question.
Go ahead, Mara. But I had something to add to Matthew's point. So yeah, I mean, one possibility is that one of the things we see with CHIME is that if you look for beams on different beams on the sky and you see something here but not here, that would be very relevant to saying that is astrophysical, right? You can make a distinction between the near field RFI and far field, an astrophysical source which is in the far field.
Oh, I just wanted to say I can't believe I don't think we've heard the word machine learning yet, like this whole conference. But I really think that machine learning can play a huge role in answering some of these questions. So, I mean, it's very easy to take bright bursts and reduce their signal to noise, or add fake bursts with different signatures to real data, and train machine learning algorithms to recognize these things in data that we might not recognize by eye. And I think in addition to using machine learning to find these more kind of unique things or place limits on the populations, it's really important that we look at all the data that's been taken from all these surveys in a uniform way, with similar techniques and machine learning algorithms. And I think there may well be lots of bursts, like Jason mentioned, like back in early surveys when we didn't really know what we were doing or what we were looking for, that are there and could be super constraining. Yeah, I didn't want to be too self-centered, but they're two grad students at WVU who might have been in touch with many of you. So Kshitij Argawal and Devansh Argawal, not related, who both they're working on this algorithm called Fetch. Well, not working on it; it's done, and so it's a machine learning algorithm to recognize dispersed bursts in data. And so they've been in touch with probably all the radio astronomers in the room who have survey data to try to get a hold of it, so it can all be processed in a very uniform way. And the aim is to maybe find a few new objects, and I think that will likely happen, although it's not a for sure thing. But the main aim is to just really improve the rate estimates, to get a very uniform, multi-frequency, volumetric rate estimate from all these surveys analyzed in a uniform way. And the code's also available for anyone to use if they want it. Yeah, I mean, you can get it now, but you can get the trained classifier once it's trained on all these different surveys at different frequencies. Then
that's actually a good segue. I'm going to jump to the third of my questions, which is this. I think this field's had already a very nice start at working together. There's the obvious point and the successful points of FRB Cat, FRB Theory Cat, FVO event, which is transitioning to this new format, and then the FRB newsletter, which disseminates results to the community worldwide. So what new activities should we be pursuing? And it's probably a little more observer-oriented than started theorists. I resonate with Jason's opinion about getting to a more common terminology and methodology for reporting observables. To what extent should we be sharing code bases and triggering phenomena and the like?
Yeah, cool. So I could take this moment to advertise this data challenge we're doing. Kendrick and I, and actually the two graduate students that Maura just mentioned at WVU. The project is called SAS. It's the sensitivity analysis for search software. The idea is there are 9 or 10 single pulse search codes around the world, de-dispersion backends plus pulse finders, basically. They're written in different coding languages. They use different de-dispersion algorithms, and they've never been compared against each other. So the idea is to simulate like 100,000 FRBs, have them all run on this common data set, and then see who emerges victorious. But really what we're doing is trying to figure out where we're kind of mutually incomplete and this sort of thing. So hopefully that'll wrap up in the next few months.
The data set, a specific telescope, or what is the...
So we're starting with the simplest possible data set, which is filter bank data with Gaussian noise and injected broadband FRBs. and then we will scale up at RFI, eventually probably have a machine learning challenge and so on.
That's a good question. Are you going to put periodic bursts in there or any kind of like quasi-periodicities and see if you can recover those with various algorithms? That would be interesting.
This first version of the challenge is really just, can you find the FRB and down to what signal to noise kind of thing.
I think that testing algorithm against algorithm is really good and really valuable. We've just had an example where we've been using a well-known pulsar package, which we think now has a bug in it, which actually reduced your sensitivity by 15%. But it was like, oh, it must be right. Everybody's using it, plowing away. The other thing that may not be known to people is that the Lorimer burst actually went through a data unloading package written by Andrew Line, and it used to look at the statistics of a 1 second block of data, and if they were not what they believed was normal, they would delete the data. So the main beam that the Lorimer burst appeared in was actually deleted by the algorithm and was only found because it was so bright that it appeared in 2 side lobes. So we wouldn't be here if the Parkes multibeam receiver wasn't in use.
To what extent should this community be coordinating on spending its resources on identifying some of these closest events? For sure, Chime must have some number of quite low DM FRBs at this stage. Should those be public sooner than the rest, or as new ones come along? Should we be begging them to make those available? And similarly, once localizations are found, should we be trying to coordinate a lot of the follow-up effort that pursues?
Yes. So a comment coming from a different community that usually follow up high energy X-ray transient since 20 years, X-ray binaries and people doing gamma ray burst or magnets or whatever. So in general, at least for this community, things started to change exactly when the GCNs started to be circulated on any kind of signal very fast. And there are a lot of people that has their own telescope, their own facility, different part of the world. So it's very difficult for a single person, for a single group, or even a single collaboration to keep track of a source in a multi-band point of view, even just because the Earth is rotating, even just because of this. So in general, from a high energy point of view, somehow this is something that can change the field in some cases, and this might be the case. I don't know.
Yes. Yeah, maybe it's directed at the 2 cosmologists on the end of the panel. Yeah, what are the cosmological applications that you think are the most promising over the next 5 to 10 years?
I would say it's really fun to think about an era where we can use FRBs as tools to understand other things. I'm kind of skeptical of the usefulness of the mean redshift DM relation to constrain cosmological parameters, since cosmological parameters have already been constrained to a few percent by the CMB and other things. And so a 1% change in that, or evolution in that mean relation will generally be degenerate with a 1% evolution of host DMs. I don't see how you'd tell the difference. If you knew that the host DMs are independent of redshift, then you could tell. But if the host DM can be a free function of z, then you're kind of stuck. I'm very optimistic about the use of propagation effects to explore new observables in cosmology, things that are a little different from the usual cosmological parameters, like background parameters, like the correlation function between different galaxy samples and matter and the electron distribution. Like Amanda was pointing out, you can measure FIGM by looking at the 2 halo term and the cross correlation between electrons and galaxies. You can also map out profiles, the distribution of free electrons around galaxies, where FRBs are kind of unique since they probe dispersion, which is an integral of 1 power of the electron density, whereas other observations like X-ray is proportional to electron density squared, or thermal SE is proportional to electron density times temperature. So the KSE can probe, or the FRBs can probe the outskirts that other things can't probe. I have the sense that there must be a ton of information in scintillation and scattering that I just can't figure out what to do with. It's probably a really underexplored thing to think about. Who knows if we detect a gravitationally lensed FRB in the next 10 years, then that could be really amazing. Like strong lensing of galaxies have our time delays are measured with statistical errors of order days, and even one measurement is really constraining. So if you imagine measuring a gravitational lensing time delay to milliseconds, that's a pretty amazing observation.
Yeah, I think I agree with a lot of what you said. I think if we are able to see a lot of FRBs to far out redshift, we'd be able to do more. The issue is just how you standardize and at the moment we have to average everything over the sky, which I think is a problem. And it's possible that when we have more Southern Hemisphere data relative to Northern Hemisphere data, we can possibly stop doing that and see differences. And that, might be interesting. I'd be excited if we could get a different value for H naught, or the same, but yeah, hey, its own value. So exactly in the middle would be very nice, but with small error bars. I think that would be good. But I think the issue is that there's so many assumptions in every single example where we try to do cosmology that I still think it's a slightly wishful thinking field. Yeah.
Can I ask, so maybe this is a question for Kendrick mostly. At what point will CHIME do like a notch of coherent D-dispersion at, say, 2000 to push out to high redshift? Because right now you're dominated by intra-channel dispersive smearing, right?
Well, we have with 16,000 frequency channels, our signal to noise loss at DM 2000 is like order 1. So if we were to do that, we would boost our sensitivity to DM 2000 events by a factor of 2 or so. Like it wouldn't be a qualitative.
Well, you're assuming something about how wide the bursts are.
So that's for narrow bursts. Because we're always limited by we always detect FRBs with incoherent D-dispersion, so we're always limited by the sample length. So at DM 2000, the DM smearing is comparable to the sample length, and there's an order 1 SNR penalty.
Okay, I thought it was worse than that, but
we have 16,000 frequency channels.
What if you just took the top 50 megs and just did a survey of that, so that you didn't wash it out with all of the potentially scattered power down the bottom?
I think we're not too suboptimal in that regard. We do search over some trial spectral indices. Our whole detection pipeline was we put a ton of time into making it super optimal under the assumption that FRBs have broadband power loss spectra, which was true a few years ago when there were like 10 known FRBs, but it was completely the wrong assumption to make, and so we're actually quite suboptimal, like you were saying with your 2 meg bandwidth FRB. We could probably, with the right software improvements, I bet we could increase our event rate by a factor of a few. But the specific problem of losing sensitivity from the bottom of the band, I think we address. We're pretty sensitive to FRBs that are just in the top.
Thanks.
I'm happy ending 10 minutes early. Any last thoughts, though, before we go? Oh, please.
So I'm interested in this FRB theory cut. So this would be classifying theory models by
you've seen advertisements of it.
quality,
Maybe it's gone by
quality and correctness. I think this would be a challenge.
Machine learning.
Yeah, maybe machine learning.
Machine learning.
Yes.
Yes. Well, you could encourage. How about the theorists probably aren't going to stick their maybe not going to stick their necks out, but you could encourage observers to say, "I've killed this theory. Here's cite the paper," and separate it.
Need a very strict prediction. Like you don't want
Yes.
like I think every theory page should have a section where you say if this is observed, I will be unable to add bells and whistles to this model to make it work or something like that. Like if let's say 121102 coincident burst, there's no whatever UV flash to some luminosity, then I'll be unable to add any more bells and whistles. It'll become ridiculous and I'll give up this toy or something like that.
That's helpful for sure. Yeah. You could separate those that have a testable prediction and those that are unfalsifiable.
Except if there are multiple sources, then just some subset don't see that, but it doesn't mean that none of them are from that progenitor, no? Like, what is the philosophy going into? Do you really expect one mechanism behind all of them? Lots of falsifiable predictions, but it's impossible to, you know, if you, like, are you ruling out any theories that have a specific polarization? No, because you see them with different polarizations. So I struggle to see how you're going to say in all of these theories, there's only one surviving.
Falsified by this event, and so if it's not falsified for this event,
exactly.
Thank you. So
said if let's say in future we find that the event rates at 10 gigahertz are kind of comparable to like 1 gigahertz, then that theory is out. It's
But if you find one object, I think
that's fine, yeah. But if we don't do it, then what's the point building theoretical models?
Yeah. I think the philosophy is that it doesn't kill doesn't kill the model altogether. Obviously, a single event. Which why could it possibly? Okay, let's stop there. Thank you, panelists.